So using our limit comparison test, we need to come up with a series that we want to compare it to, that we know whether it converges or whether it diverges. And so how do we normally determine what series to try to compare it with? Anybody remember? Just take a look at the base power up here. The base power up here is n, and the base power down here is n cubed, right? That's our, look like an n cubed. I'm going to fix that so it looks like an n cubed. There we go. So n over n cubed is 1 over n squared. So we're going to want to compare it to 1 over n squared. And, you know, we have to have all positive terms. And so if we're looking at values of n, as long as n is greater than 1, which it is, right? This is going to be 4 minus 2 plus 1. That's positive, and the numerator is going to be positive. So we know these are all positive terms. We know that 1 over n squared has all positive terms. And so we should be able to just not directly, but use the limit comparison test on these by setting up the ratio for the limit as n approaches infinity of our series, so 7n plus 3 over 4n cubed minus 2n plus 1 over 1 over n squared. And since when you flip that around, that becomes the limit as n approaches infinity of 7n cubed plus 3n squared over 4n cubed minus 2n plus 1. We'll recognize that the limit of this is equal to 7/4. And since 7/4 is a value that is less than infinity and greater than 0, either these series both converge or they both diverge. And since we know that the sum from n equals 1 to infinity of 1 over n squared converges by the p-series test, then the sum from n equals 1 to infinity of 7n plus 3 over 4n cubed minus 2n plus 1 also converges. Does that make sense, Adrian, and everybody else? Yep, everyone's good. Cool. All right. So, anything else in general that you guys would like to talk about? If not, I'm going to just sort of work our way backwards through some of these free response questions, looking at some of the more difficult, you know, the series ones and stuff first, and then continuing back through all the other topics until we kind of run out of time. Anybody else? Anything specific? Population growth questions. Okay. Do you have a specific one in mind, Elon, or should I just do one? Okay, just in general. Okay. Let's see here. I'm pretty sure I saw one in here when I was throwing all this together. Yeah, you should know the equation for logistic growth. Yeah, Adrian, you should know what the differential equation looks like, and you should know what the solution to the differential equation looks like. Sometimes they might ask you to solve a differential equation that looks like that using the partial fractions. And if you just know the formula, you can just do it, and it saves you a ton of time, especially if it's in the multiple choice. But it does occasionally show up. So yeah, you'll want to know that. Let's see. This is a logistic growth line. You think it's you're talking about something like this one, Elon? Yeah. Okay. Let's do this one then. So we've got. I'll give you guys a second to read through it, and then we'll just sort of work through it and see what we can do with it. So basically, we've got a virus that's in a host somewhere, and the amount of that virus, or the population of that virus, can be satisfied using this differential equation, dA dt equals t minus 1/5 A. And A is millions of virus cells, T is days from 5 to 10. And we know that at T equals 5 days, there's 10 million cells of the virus in the host. So for part A here of this free response, we want to write an equation for the line tangent to A at T equals 5. So we're going to do that, and noting that A is measured in millions of virus cells, that'll tell us that the point that we're looking at is the point 5, 10, since it's 5 days and 10 million cells. We'll write our tangent line using a slope. Our slope will just come straight from our differential equation. So dA dt equals your t, so 5 minus 1/5 of 10, which is 2. So that should just give us a slope of 3. And so our equation for our tangent line should be y minus 10 equals 3 times 5, and then they say approximate that at 7. So approximate that at 7 just gives us 2 times 3 is 6, plus our 10, which gives us 16. So part A, pretty easy. And make sure you get the right units. There are 16 million cells, right? Everybody good with part A? All right, part B says show that A of t equals this satisfies the differential equation with the initial condition that A of 5 equals 10. Well, in order to show that, all we're going to have to do is just take a derivative of this function and show that it gives you t minus 1/5 A, and also show that it actually contains this 0.5, 10. So first thing we'll do is figure out if A of 5 actually equals 10. So A of 5 ought to be negative 25 plus 25 plus 10 e to the, what does that become here? If we got our t is 5, that's negative 1 plus 1, so 0. So 10 e to the 0, so that's just 10. So first off, yes, it satisfies the initial condition. And then the second thing that we'll do is we will show that the derivative of that equals t minus 1/5 A. So we get 5 as our derivative there. Our derivative of 10 e to the negative t over 5 plus 1 is plus 10 e to the negative t over 5 plus 1 times the derivative of negative t over 5 plus 1, which should be negative 1/5. And then we will multiply that negative 1/5. So we're going to end up with 5 plus, actually, sorry, 5 minus 2 e to the negative t over 5 plus 1. And then from there, we have to go back in here, and since our dA dt is actually t minus 1/5 A, we're going to have to find out what 1/5 of A is. So 1/5 of A is negative 25 plus 5t plus 10 e to the negative t over 5 plus 1 divided by 5. So that's going to give us negative 5 plus t and plus 2e to the negative t over 5 plus 1. And so this thing that we just got for 1/5 A, does this, what we got for dA dt, equal t minus this, negative 5 plus t minus 2e to the negative t over 5 plus 1. And the answer there should be that it, hopefully that it does. So we have the t minus, that t will cancel out. The negative 5 is going to give us a positive 5. And then we end up with, let's see here. That was a positive 2 there. So that should be a positive 2. Minus 2e to the negative t over 5 plus 1. So checks out that they equal each other. Everybody good with part B? Yo-wah. That's right, Adrian. Yo-wah. All right. Part C. I need a new page for part C. Part C says that the host is receiving an antiviral medication. The amount of the medication in the host is modeled by M, which satisfies dm dt equals -1/2 m over t plus k, where m is milligrams, t is days since it received it, k is a constant. We want to know is the amount of medication in the host, or if the amount of medication in the host is 30 milligrams at time t equals 0 and 15 at t equals 3, we want to figure out what m of t is in terms of t. So in order to do that, we're going to have to solve this differential equation. And the right way for us to solve that differential equation is to separate the variables. So I'm going to go to a new page for this. What do we have? dm dt equals -1/2 m over t plus k. Sorry, 1 second. My kid's asking me something. Okay, sorry about that. All right, so we need to separate the variables. So when we separate the variables, we're going to get dm over m equals -1/2, or negative, we'll say -1 over -1/2 times 1 over t plus k dt. And then we'll need to integrate those. And so both of those should integrate fairly easily. Natural log absolute value of n. This one is just a -1/2, and then this one becomes natural log absolute value of t plus k plus some constant. Everybody good with that? So far? Okay, so then that k is it's a constant within this problem, within the differential equation that's already there. So we're going to have to find that constant for k, and we're going to have to find this other plus c that we get from the integration. So the k is just there from the differential equation from originally. Does that make sense, Adrian? Okay, cool. So first thing that we'll do is we will plug in one of our initial conditions. Our first initial condition is at t equals 0, we have 30 milligrams. So at t equals 0, there's 30 milligrams. So the natural log of 30 equals -1/2 natural log of k plus our c. And let's see here. I think it might be, yeah, I don't know. Maybe it doesn't really matter. It might be helpful for us if we write this -1/2 on the inside here. So let's do this. Natural log of 30 equals the natural log of 1 over the square root of k plus our constant. And we know that that's going to all be positive stuff there. And so from there, we should let's go back to our other initial condition that at t equals 3, it's 15. And if at t equals 3, it's 15, we end up with the natural log of 15 equals -1/2 natural log absolute value of 3 plus k plus our constant. And we could rewrite that as natural log of 15 equals the natural log of 1 over the square root of 3 plus k plus this other constant. And these constants should be equal to each other. So if we go through and solve for both of the c's in each one, we should get natural log of 30 minus natural log of 1 over root k equals natural log of 15 minus natural log of 1 over root 3 plus k. And let's see here. That should help us figure this out here now. So natural log of 30 and natural log of 15, if I subtract the natural log of 15 over, I'm going to get natural log of 30 minus natural log of 15. What's the natural log of 30 minus the natural log of 15? Should be the natural log of 30 over 15, which should just be the natural log of 2. So we're going to have natural log of 2 equals, and then the same thing here, we're going to add this one over. So we're going to get natural log of 1 over root k minus natural log of 1 over root 3 plus k. So that's going to give us natural log of root 3 plus k over root k. And that tells us that 1 over k should be 1 over k, sorry, 1 over root k over 1 over root 3 plus k, which should give us the root 3 plus k in the numerator. Yeah, that's all right, Adrian. And then from there, we just need to figure out what makes 2 equal the square root of 3 plus k over k. Well, it sure looks like that'd be a value of k equals 1. And so 3 plus 1 over 1 is 4, and the square root of 4, you get 2. And so k is 1. And if k is 1, then we can go back over here and find that the constant that we end up with, this c, equals the natural log of 30, because the natural log of 1 is 0. That cancels out, and you get constant of natural log of 30. So our final thing that we're going to look at here is natural log of absolute value of n is equal to negative 1/2 natural log of t plus 1 plus ln 30. And then we'll exponentiate both sides. And the amount of the stuff is always going to be positive, so we don't need to worry about whether it's positive or negative on the right. It's just going to be a positive when we clear up the absolute value. And if we want to, we'll pull the 30 out as a constant in front for the e to the natural log of 30. And then this is e to the negative 1/2 natural log absolute value t plus 1. Or if you want to write it as 30, because we adjusted this before, 30 e to the 1 over natural log of 1 over root t plus 1. Either of those would be fine. Oh, sorry, there's no natural log there anymore. That's my fault. Should have. That's I simplified it. Yeah, let's simplify that all the way. E to the natural log of something is just that thing. So this just becomes 30 over root t plus 1. If we bring that negative 1/2 in, 30 e to the 1 over root e to the natural log of 1 over root t plus 1 just becomes 30 over root 1 plus t. Good or no? That was a kind of complicated one to get through, having to set up the system of equations to solve it. But if you left it as this, I think you're fine, or this, I think you're fine. I mean, this is nice, but yeah, it's always nice to simplify it. This is not wrong. It's solved for n. It's done what they asked you to do, so they should give you points for that. Does that help you, Elon, or no? With the population thing, it's not like an actual population of people, but population of virus. Okay. Anybody else? Any other specific types that you want to talk about? Sure, logistic growth one. This one sure looks like it's a logistic growth. Let's do this one. So I'll give you guys a second to read through that one, and then we'll start working through it. All right, so talking about fertilizer, and they're injecting liquid fertilizer into hydroponic growing system via a pumping system. It's too bad that Ryan's not here to talk about his hydroponically grown tomatoes. Anyway, the amount of liquid fertilizer that's injected into it is modeled by this logistic differential equation. df/dt is 1/3 f times 6 minus f. We know it's logistic, not just because they say it's logistic, because it's k times the variable f, and then m minus that same variable f, not the variable in the denominator, not the t, but the amount of the population. That's what we usually use, but this time it's the amount of fertilizer. We're given an initial condition that at t equals 0, there's 3 liters that are injected into it, and then give us a note about what hydroponics is. Very exciting. All right, so part A is something that I talked about in the last session with logistic growth, about these limits that they often like to ask about, and so here they've asked about them. The limit as t approaches infinity of capital F of t, so the solution to this, well, the solution to the differential equation will always be approaching the carrying capacity, and the carrying capacity is always m, and so that's just going to be 6. That should be pretty straightforward. And then for the one as t goes towards infinity of df dt, that limit should always 100% of the time be equal to 0, because the function f itself is approaching a horizontal asymptote as t goes towards infinity. In fact, in this case, the horizontal asymptote of y equals 6, which is why we got 6, or f, f of t equals 6 or whatever. And so the rate as we approach infinity, though, is approaching 0, because we're narrowing out and hitting that horizontal asymptote. So the rate of change is becoming like a horizontal line. It's becoming like 0. Everybody good there with part A? Okay, part B is another thing I talked about quite a few times, is that F increases most rapidly. This is always at half the carrying capacity. And so with some very basic arithmetic, that should be 3. Everybody good with part B? Okay. And then for part C, we're looking for the second derivative here. So our second derivative, if df dt equals 1/3 f times 6 minus f, they're going to ask us to take a derivative with respect to t. So we're going to get product rule here. So that'll be 1/3 of f times the derivative of 6 minus f, which is negative df dt, plus 1/3 df dt times 6 minus f. And then we can factor out the df dt from each of these and simplify stuff down. You don't have to factor out the df dt if you don't want to. You can just replace each df dt with 1/3 f times 6 minus f. And in fact, let's just do that. 1/3 f with a negative out in front times 1/3 f times 6 minus f, plus 1/3 of 1/3 of f times 6 minus f times 6 minus f. So a lot of 1/3s and 6 minus f's and whatnot, but we end up with negative 1/9 f squared times 6 minus f plus 1/9 f times 6 minus f squared. And if you want to factor that all out nicely, you get 1/9 f times 6 minus f, and then times, this one's got, if you took out the 6 minus f minus f. So our final simplified down answer should be 1/9 f times 6 minus f times 6 minus 2f. Good with that or no? And if you really wanted to, you could factor out a 2 from this, but I don't see any particular reason to do that. Yeah. All right. And then, let's see, it says, it just says to find it. Okay, and then it says to use Euler's method, starting at t equals 0 with 2 steps of equal size to approximate the amount in the growing system at t equals 1. So using Euler's method, we're going to start at 0, what was it, 0, 3? Yeah, 0, 3. And we're going to do 2 steps. So we're just going to go 0 to a half and a half to 1. And so this is our first point, and then normally we look for our dy dx, or in this case, it's our df dt, which ought to be, now I've forgotten what it was. What was it? 1/3 of f times 6 minus f. So if f is 3, that's going to be 1/3 of 3, which is 1, times 6 minus 3, which is 3. And we're going to multiply that by our step. Our step is a half. And so that's going to mean that we're going to increase our value for f by 3/2. And so our next point will be 1/2, and that'll be 9/2. Everybody good with the first part of that there? Hopefully. And then the second time, we're going to get 1/3 of 9/2 times 6 minus 9/2, which is 3/2, which the 3's will cancel. That ought to give us a 9/4 there. And so multiplying our 9/4 by our step of 1/2 ought to give us 9/8. And so we ought to be at 1, comma, whatever 9/2 plus 9/8 is. What is that? 45/8. And that would be our answer for part C. And first part D. Right? Yeah. And then we want to know, is that approximation an overestimate or an underestimate? And so the easiest way to do that is to figure out whether our function is concave up or concave down on that interval. And so we've got I don't know. I haven't done it yet. I don't know. We'll have to see. I haven't actually plugged it in to see if the function is concave down or concave up. So at the point where it's 0, let's say 0, 3, that's going to give us what? 1. Oh yeah, we already. Oh no, our second derivative. What's our second derivative? Our second derivative was this. So we'll evaluate this at 0, 3. So that's going to be now at 0, 3, that comes out to be 0, doesn't it? Yeah, true. That would make sense at 0. Yeah, that's true. Up to 3, it's concave up, and then after 3, it's concave down. Right, so at 3, switches concavity. So since we're using tangent lines and we're finding the value after 1 month, we're looking at, these tangent lines are always going to be a little bit below, and so it should be an underestimate. Good or no? Yeah, you're right. Up till this is 3. Yeah, that's true. Up till 3. So it's an underestimate here and it's an overestimate here. And since our value is greater than 3, 45/8, that falls over here where these are overestimates. So yeah, you're right, actually. I screwed that up. Should be an overestimate because those are the y values of, or not y values, but the values of f that are greater than 3. And the values of f that are less than 3 over here is an underestimate. Values of f over here are greater than 3, makes it an overestimate here. And since our value is greater than 3, that makes sense. Any questions on that one? That was it for part D, right? There was nothing else to part D. Yeah. Cool. Anything else in particular that you guys would like to talk about? All right, serious ones it is, Adrian. We'll just start with this one. So I'll give you guys a second to read through it, and then we'll start working our way through it as well. So we're given a Maclaurin series for f is x minus x cubed over 3 factorial, x to the 5th over 5 minus x to the 7th over 7, and so on. They've given us the formula for it there. We should know what that formula represents, right? What does that one represent? Yeah, that's correct, Adrian. That one should be signed. All right, good. So we want, though, f of x squared. So all we have to do is replace the first 4 non-zero terms with x squareds and replace the x in our general term with an x squared. So our first 4 non-zero terms ought to be, instead of x, it should be x squared. Instead of x cubed, it should be x squared cubed, which will be x to the 6th. Still over 3 factorial. And then it should be x to the 10th over the 5 factorial. And then it should be minus x to the 14th over 7 factorial. Everybody good with those terms? And then your general term ought to just be negative 1 to the n. And since it's x squared to the 2n plus 1, that'll be x to the 4n plus 2. All over still just that 2n plus 1 factorial. Everybody good with part A? All right. Part B, the limit as x approaches 0 of x squared minus x to the 6th over 6 minus g of x. Okay, so, and all over x to the 10th. So if we're looking at this for a limit here, let's first try to figure out what x squared minus x to the 6th over 6 minus g of x over x to the 10th looks like. Well, it looks like x squared minus x to the 6th over 6 minus, well, all of this again, right? X squared minus x to the 6th over 6 plus x to the 10th over, well, 5 factorial is 120 minus x to the 14th. I don't know offhand know what that is, so we'll just write minus 7 over 7 factorial, and so on with our general terms, right? And we're going to divide all of this by x to the 10th. So the first thing that we will note then is that this becomes, well, x squared minus x squared cancels. Negative x to the 6th over 6 will cancel with the plus x to the 6th over 6. we end up with a negative x to the 10th over 120. Well, that x to the 10th over 120 is going to be divided by x to the 10th. So that's going to be the limit as x approaches 0 of negative 1 over 120 plus, well, all these other terms have x to the 14th, right? If I take x to the 14th and divide it by x to the 10th, that's going to give me x to the 4th. And the next one, which will be x to the 18th, will become x to the 8th. They're all going to have an x to a power in them, right? Power greater than 0. And since we're evaluating at x equals 0, those are all going to just become zeros. And so this should just come out to be negative 1 over 120. Good or no? All right, part C. Part C is just asking us to write out the series for h and then use the first two terms of our answer to approximate h of 1. So h is just the integral from 0 to x of g of t. So let's write this out. Let's say that the integral from 0 to x, we'll say h is equal to the integral from 0 to x of our function g, and we'll write it as g of t. So that'll be of x squared minus x to the, or we'll say t squared minus t to the 6th over 3 factorial plus t to the 10th over 5 factorial. How many, we wanted 4 non-zero terms, I assume, again? Yeah, okay. So minus t to the 14th over 7 factorial plus, and we had a t to the, we had a negative 1 to the n, t to the 4n plus 2 over 2n plus 1 factorial. And so we'll integrate this. And when we integrate it and evaluate it as x, that should become x cubed over 3 minus x to the 7th over 7 times 3 factorial, which is 42, plus t, I don't know why I'm writing t, plus x to the 11th over, this time I'm just going to write 11 times 5 factorial because I don't feel like doing the arithmetic on that, even though it's not that hard, minus t x to the 15th over 15 times 7 factorial, and so on. And the general term should be negative 1 to the n, t to the x to the 4n plus 3 over 4n plus 3 times 2n plus 1 factorial. And then when we evaluate all of these things at all of the integrals of this at 0 is just 0, right? And so this is our 4 non-zero terms in our general term. Everybody good with that? The first part of part C? Okay, and then it says use the first two terms to approximate h of 1. So we're going to write 2 down here with just using 2 terms. So Adrian just asked if it was 1 to x, what would you do? Well, if it was 1 to x, you'd have to, you'd literally have to write out minus 1 over 3 factorial plus 1 over 5 factorial minus 1 over 7 factorial. Effectively, you just end up with this term at the end that would become a minus, you'd have a minus 1 to the n over 2n plus 1 factorial would be an additional term out there at the end, which would be a non-zero term that you'd throw at the beginning. Does that make sense? You just have to put this constant. They're not going to ask you to do it as something that doesn't make this come out to be 0 at the end. So if they asked you from 1 to x, you'd have to, they wouldn't ask you that, but if they did, you'd have this extra minus negative 1 to the n over 2n plus 1 factorial at the end. What they might ask you to do is find the indefinite integral of it. If you ask you to find the indefinite integral of it, then you have to put a plus c and solve for the constant based on some initial condition that you could figure out, which you should be able to figure out would be that if x was 0, then the value of this series would be 0. And so you'd plug in 0 to find out that your constant is 0, and you'd still just get this. But they won't ask you from something that doesn't work out nicely here at the end to just either a 0 or just one single value. All right, so h of 1 using two terms should be 1/3 minus 1/42. And the third minus the 42nd, let's see, what is that? That's 14 minus 3, so 11. And not 14 minus 3, 14 minus 1. I don't know why that was, yeah. I don't know why I tried to multiply that one by 3 also. So 11 over, I just said it's not 11, it's 13. 13 over 42. So that's our approximation using a second degree Taylor polynomial truncation there. And then it wants us to know in part D, explain why that approximation in part C differs from the actual value of h of 1 by less than 1 over 1,000. So we'll note that we truncated after two terms here. And since this is an alternating series, we'll use the alternating series error bound, which will tell us that the truncation is always, the error is always less than or equal to the next term, which in this case is 1 over, that's, what did I say, 11 times 120, which I refused to do earlier, but what does that come out to be, 1320? And so our error is less than 1 over 1,320, which is less than 1 over 1,000. So therefore, our error must also be less than 1 over 1,000. Does that make sense to everybody there for part D? Should we do another series one? Let's do this one. This one's got the Lagrange error bound, which nobody usually likes. So let's do a Lagrange error bound one here. Let's take a look at this Taylor series for a function f around x equals 0, where we are given the series k equals 1 to infinity of 2 to the k times x to the k over 3k. So to do part A, which says find the fifth derivative of f at 0, that means we're going to have to write out our terms of our series to figure out what the coefficient is going to be. So if we start at k equals 1, our first, that's going to give us what? 2/3 x, divided by 3, 2/3 x, and then we're going to have with our k equals 2. I guess we don't need to write them all out. I'm not going to write them all out. We'll just write out the fifth one. I thought we'd maybe write them all out because we might need them, but what's the point? 2 to the 5th times x to the 5th over 3 times 5. All right, and so that ought to give us 32/15. But recognizing that the denominator also has to have a 5 factorial in it. And so that's going to give us a 120 down here. And so what does that come out to be if we simplify all of that out? Oh, sorry, I shouldn't put the 120 down there. So the term itself is this, which should equal it should equal the value of the derivative. Yeah, I always screw these up as I try to write these in here. This needs to have a 1, because there would be a 120 in the denominator, we have to multiply this by 120 to figure out what it comes out to be. Does that make sense to everybody or no? Why we need to do that? Because normally it would have that 120 in the denominator, 5 factorial. But this series itself comes out to be this. Everybody good with multiplying that by the 120? I hope. What does that come out to be? 256? So that comes out to be 256. You all good with part A or no? Nobody's saying anything now. You're understanding why I multiplied by 120 or not? Yes, I can explain again. So the term that we get, so like our fifth degree term should be, it should be the fifth derivative at 0 times x to the fifth over 5 factorial, right? That's what we should get. And we get this. So the x to the fifths are insignificant. So we end up with the fifth derivative at 0 over 120 equals 32 over 15. And so we multiply the 32 over 15 by the 120. That, with the written out work, does that make more sense to everybody? Right, fifth derivative at 0, x to the fifth over 5 factorial is the fifth term of that series. And so the fifth term of that series is 32/15 x to the fifth. The x to the fifths cancel. And then you just solve for the fifth derivative of f at 0. Good or no? Adrian, you're good. Elon, you good? Elon, are you good now or no? Yes, the fifth term is 32. So I'm going to write down here. The fifth term is 32 x to the fifth over 15, right? That's what the fifth term is. The fifth term is found by taking the fifth derivative at 0. This is how we find the Taylor polynomial, the Taylor series, right? By doing this, right? The fifth derivative at 0 times x to the fifth over 5 factorial. And so the x to the fifths cancel each other out. We're left with 32/15 equals the fifth derivative of f at 0 over 120. So we have to multiply by the 120 to figure out what the fifth derivative of f at 0 is. Okay, cool. So I assume the rest of you are good since you never said you weren't good. Alice, Ashley, Delphine, you're good. Okay. All right, so that's part A, 256. Part B just asked us specifically to use the ratio test to find the interval of convergence. So I'm going to write the series again here on the next page. K equals 1 to infinity, 2 to the k over 3k times x to the k. And so if we're going to find the interval of convergence for this, all we need to do is use our ratio test like it asked us to do. Limit as k approaches infinity of the k plus first term, so 2 to the k plus 1, x to the k plus 1 over 3 times k plus 1, divided by the original series, which would be multiplied by the reciprocal of the original series, 3k 2 to the k, x to the k in the denominator. And then we'll simplify those. And because this is not always positive, we'll use absolute values on it. And so we have the limit as k approaches infinity of, well, 2 to the k plus 1 over 2 to the k is just a 2 in the numerator. X to the k plus 1 over x to the k is just an x in the numerator. And then 3k is just 3k, and 3k plus 3 times k plus 1 is just a 3 times k plus 1, or a 3k plus 3. And the limit as k approaches infinity of that, well, the degree of the k's is the same. So 3k over 3k plus 3 just cancels out to be 1. And this gives us a limit of the absolute value of 2x. Everybody good with that? And based on the ratio test, we set that less than 1 to get that the absolute value of x is less than a half, or that the base interval of convergence for this is between -1/2 and +1/2. but we have to go in and we have to check our endpoints to determine if it actually converges at those endpoints. So we will first, I think I have room over here. First, we'll say at x equals -1/2, we are looking at this series, the sum from k equals 1 to infinity of 2 to the k, -1/2 to the k over 3k, which should be, well, 2 to the k and 1/2 to the k. Those should just cancel out and become 1 to the k, or just 1. So we end up with a -1 to the k in the numerator and a 3k in the denominator. And what do we know about that series? It should converge by the alternating series test. Everybody good with that? And at x equals 1/2, we're going to end up with the series 2 to the k, 1/2 to the k over 3k, which equals 1 over 3k, series from k equals 1 to infinity of 1 over 3k. And that one we can say diverges by the p-series test. And therefore, we will say that our final interval of convergence here is -1/2 is less than or equal to x is less than 1/2. It does not ask about absolute convergence. It doesn't ask about conditional convergence. It doesn't specifically ask for the radius of convergence, so you don't need to list those things. If it asked about absolute convergence, it would only converge absolutely on this interval, because the absolute value of this series just becomes 1 over 3k, which diverges. So it converges conditionally at -1/2. It converges on -1/2 to 1/2, converges absolutely on the open interval -1/2 to 1/2, and then the radius of convergence is 1/2. Does that make sense to everybody? Is that the last part of that one? Or is there another part to that one? Oh, there's 2 more parts to that one. Okay. Part C, use the second degree Taylor polynomial for f about x equals 0 to approximate f of 1/4. So our second degree Taylor polynomial, we need to write out those first 2 terms. So let's see here. The sum was from k equals 1 to infinity. I'm just going to write the series again so I don't forget it. 2 to the k, x to the k over 3k, right? So the first term should be 2/3 x. The second term should be, we plug in 2, should be what? 4/6. So again, 2/3 of x squared. Everybody agree with that? We're going to evaluate that at x equals, was it a 4th? It was a 4th. Yeah. So at 1/4, that just becomes 2 over 12, which is 1/6. And it becomes 2 over 48, which is 1 over 24, which looks like it comes out to be 5/24. Everybody okay with part C? Now, the second one is also 2/3, just because when you plug in 2, right, plug in 2, you got 2 squared, x squared over 3 times 2. That's just 4/6. Yeah. Just the arithmetic. In the denominator? No, it's just 3 times k. Yeah. All right. What did part D ask us? Part D gives us some information about the third derivative of f. So we know that the third derivative of f on the interval -1/4 to 1/4 is always less than or equal to 128/3. We want to use the Lagrange error bound to show that the approximation from C differs by less than 1/9 from the original value of f of 1/4. So the Lagrange error bound, remember, says that the error is less than or equal to the third, well, not the third, but in this case, the third, the next derivative at some value c between x and a. In our case, a is 0 for us, and x is 1/4. Right? A is 0 because our series is centered at 0, and x is 1/4 because that's the value we're evaluating it at. So we know that we want the third derivative at c, and the value of c that makes this the largest between 0 and 1/4, times x minus our a, or just x, to the third over 3 factorial. So our error is going to be less than or equal to this. This is the bound on our error. And so they tell us that the third derivative between negative 1/4 and 1/4, which includes our interval 0 to 1/4 here, is always less than or equal to 128 thirds. So the max it could possibly be would be 128 thirds. Our x cubed is just our 1/4 cubed. And then we also have a 3 factorial in that denominator, which is a 1/6. And so then we just need to simplify out this wonderful little fraction that they've given us and show that it must equal, we hope, 1/9. Okay, well, if we simplify this down, that should make sense, because if we factor out the 4 cubed, that's 2 to the 6th, times another 2 here would be 2 to the 7th, and 2 to the 7th, 2, 4, 8, 16, 32, 64, 128. We've really got 128 over 3 squared times 2 to the 7th. If you do the prime factorization down there in the bottom, 128 over 2 to the 7th is 1, which is 1/9. So we've shown that our error is less than or equal to 1/9. Good or no? Everybody understands how the Lagrange error bound works there? We want to do one more series one. I think I've got one more that I threw up here. Yeah, we got one more series one. You guys want to do this one too? All right, let's do this one. So here we have 1 over n to the p, and we should know about, we know what makes p diverge, right? P will diverge, or sorry, into the p, whatever into p will diverge if p is what? If p is exactly, p is less than or equal to 1. Okay, so we want to know, does the series from n equals 1 to infinity of 1 over n to the p squared diverge? And then we need to justify our answer. So there are there are values between 0 and 1 here. If I take a value between 0 and 1, that should give us, when we square it, still something that's between 0 and 1, right? And so p being less than or equal to 1 means that if we're talking p less than or equal to 1 greater than 0, we've got p squared is still less than or equal to 1, then it should diverge. And we don't normally talk about p values that are negative here because that's not really 1 over n to the p. So really we should just be saying that's greater than 0 there. Everybody good with part A? And there's not much to say there other than that if you square a number that's between 0 and 1, it stays between 0 and 1, and so it must still diverge. And you'd say because of the p-series test. Yeah. Everybody okay with that or no? All right. Then for part B, we want to know if the series from n equals 1 to infinity of negative 1 to the n over n to the p plus 1 converges absolutely, conditionally, or if it diverges. So we should know a few things already. One, that p plus 1, if 1 over n to the p diverges, that means that p was between 0 and 1, which tells us that p plus 1 must be greater than 1, guaranteed, right? And so really what we're looking at here is an alternating series that if I plug in a value of p into this, I'm going to get something that has power of greater than 1 in the denominator, right? And so we would need to note that both the series from -1 to the n over n to the p plus 1 converges by the alternating series test. And you don't even really have to say that. You should be able to say that the series from, I guess I should write n equals 1 to infinity on these, of n to the p plus 1 converges by the p series test. And since that one, I mean, yeah, this series is always going to be positive. And so if it's always positive, then it's good to say them both, but if the absolute value of a series converges, then the series itself converges. So that would work as well. So we would say that this converges absolutely. Everybody good with that converging absolutely? That was a pretty straightforward one. Cool. All right. And then we want to evaluate the integral from 1 to infinity of 1 over x to the p plus 1. So I'm going to write this over here. That is what it said, right? 1 over x to the p plus 1 to infinity. Yeah. All right, so in order to do this integral, we first are going to recognize that this is an improper integral, and that if you do not rewrite this as something like the limit as a approaches infinity of the integral from 1 to a of 1 over x to the p plus 1 dx, it will give you no points. If you don't rewrite your improper integral as a limit, you will get 0 points on any free response question that involves an improper integral, guaranteed. So make sure you rewrite. Okay? So then we just need to integrate this. Well, I mean, how do we integrate 1 over x to the p plus 1? If this power down here is a number that is, we know that this number down here is greater than 1, we could rewrite this as the limit as a approaches infinity of what? Could do x to the negative p plus 1, and then we could just use the power rule, which should give us the limit as a approaches infinity, well, x to the negative p minus 1, and if we distribute that through, it should just go up to x to the negative p, and then we'll divide by negative p, and we'll evaluate that from 1 to a, and if we want, it might be nice to rewrite this. Well, we'll just drop this down to the denominator as we do it. This becomes negative, and then the x will drop down here, so this becomes negative. And then we have 1 over a to the p times p, and then minus, and then we have another negative here, so it really becomes a plus. And then we've got a, as we drop that 1 down, that just becomes a x to the negative, or x to the p, which is just a 1 to the p, which is just a 1. And so we end up with a 1 over p down there. And as a goes towards infinity, we should see that a to the p should be going towards infinity, which means that this whole denominator is going towards infinity, which means that this whole first part of the term is going towards 0, and we end up with a value of 1 over p. Everybody good with that? Any questions on that? Are these helpful? Do you guys think these are helpful? This is good or no? Okay, Adrian says it's helpful. Wonderful. All right. That's all the series ones I had up here. So we've got, let's see here. I don't know, would you guys prefer to do like a vector problem or one of these like polar area or a that's still the polar one, a non-polar, like, perimeter, arc length type thing with volume and stuff? What do you guys think? Vector or that, or you don't care, or something else? Any thoughts? Any preference? First preference I see, polar area, arc length. Okay, that's what you're all saying. All right, we'll start with the polar area, then we'll do this arc length one right after. So, all right, here we go. Polar area. So we have two curves here. Well, one is cosine theta, which we should know which one is cosine theta. Cosine theta should be, yes, the one on the right, smaller circle, the one that's in the quadrants where cosine is positive. And then our sine, 2 sine theta one is our bigger circle. And so we are then looking at the region S that's between the two of them. We want to find the area of S. So the first thing that we need to do to find the area of that is what? What should we do with that? We need to figure out where they intersect each other. We should know that they intersect each other at the origin, and that at the place where cosine theta is equal to 2 sine theta. And what theta value gives us that? When does sine theta equal to, cosine theta equal to sine theta? Anybody got a calculator on them? Otherwise, I'll type it into Desmos and figure it out myself. But let's see here. Nope. Okay, so let's see here. I'm typing it on my phone here. Looks like they're going to intersect at point, what is it? 0.464. And your graphing calculator will give you more decimals than just 3 decimals. So make sure you use more than just 3 decimals for the intermediary values. So then if we're looking for the area of S, and we know that they intersect at 0 and they intersect at this 0.464 value, how are we going to figure out this area? Well, from 0 to that 0.464 value, the theta value of 0, we're getting stuff that is specifically on the larger curve, which is our 2 sine theta. So we should be able to write this as 1/2 the integral from 0. I'm going to just call this b, so I don't have to keep rewriting, from 0 to b of 2 sine theta squared, right? 1/2 r squared d theta. And then as we go from b equals 0.464 around to pi over 2, because pi over 2 is when the cosine graph should hit 0 at the pole. That should give us our other one, cosine squared theta d theta. And so from 0, because a theta value of 0, our cosine graph is over here, right? But we know that they're going to intersect still here at the pole. There's still a place where they intersect there, which is when we're at 0, a theta value of 0 for sine, but a theta value of pi over 2 for cosine. So the lower piece of that little thing that I sketched in blue comes specifically from the cosine curve, and then the upper piece here specifically comes from, sorry, this one, the smaller piece comes specifically from the sine, and the larger piece comes specifically from the cosine. that make sense to everybody? And you'll just add those two integrals together. Cool. Let's see here. I'm typing it in on my phone here to see what this integral comes out to be, unless somebody's got it. Looks like it comes out to be 0.240. Everybody good with that? Okay. All right. Part B, there's a point on the graph of R2 where the slope of the line tangent to the graph is tangent of 2. So we're looking at 2 sine theta. And we want to figure out, we know that dx d theta equals 2 cosine 2 at that point, so we want to find dy d theta. So if the slope of the tangent line is tangent 2, so we'll write that out. Tangent 2 is dy dx, right? That needs to equal dy d theta over dx d theta. And it tells us that dx d theta is 2 cosine 2. Dy d theta over 2 cosine 2. Well, dy d theta must equal, looks like it should be 2 sine of 2. Otherwise, there's no way to make that true. Everybody good with that? And 2 sine of 2 is good. You wouldn't have to put a decimal if you don't want to. Unless, I don't think it says to. Yeah. Easy enough? That's pretty easy. You just got to know, recognize that the slope of the tangent is dy dx, and recognize that that's dy d theta over dx d theta. All right, so now we've got a new polar curve that is defined as the first curve plus the second curve. From 0 to pi, we want to find the greatest distance from any point on the graph of R to the origin. So we should know that the distance between that graph and the origin is should just be whatever that, what is that function? Sine 2 sine theta plus cosine theta, right? And so if we are looking for the maximum distance, we just need to find the derivative. We had room here. Oh, geez. There we go. Where did the work go? Did I just delete that page with all the work we did? Page disappeared. There it is. All right. Let's try this again. So the distance was cosine theta plus 2 sine theta. To find the maximum of that, we need to find the derivative of that, which is negative sine theta plus 2 cosine theta. We need to figure out when does that equal 0. Once again, you'll type that into your calculator to find the x-intercepts of it, or you'll set sine theta equal to 2 cosine theta, one or the other. And when does that come out to be true? Anybody got a value there? Looks like 1.107, according to Desmos for me. 1.107, and then we would need to show that this is a max. So we'd either have to pick a value to the left and a value to the right and plug them into our derivatives, or we'd have to take a second derivative and evaluate it. This, I think it's easy enough to just do a sign chart here. If we plug in 0 to our derivative, we end up with 0 plus 2, so that's positive, so it's increasing. And if we plug in pi, we end up with 0 minus 2 decreasing. So it's a max at theta equals 1.107. Everybody good with that? All right. And then we want to do this one right here. Does that one look good to everybody? People said they wanted arc length. All right, so for part A, we're going to find the area of that region in terms of K. And so we have, let's see, what x equals 1, x equals K. And this is the function 1 over x. So to find that area, we just need to integrate from 1 to K, 1 over x dx. Should be pretty straightforward. Right? Natural log absolute value of x from 1 to K just gives us natural log of K. Everybody good with part A? Pretty straightforward. Okay. Part B, we don't need to evaluate it, but we just need to write an expression that gives us the perimeter of R. So the perimeter should be whatever this is, that'd be f of 1. So this is 1 unit plus whatever this is. Well, that ought to be k minus 1 plus whatever this is. Well, that ought to be 1 over k. And then plus this piece right here, which this is our arc length formula that we need to be able to set up. So what does our arc length formula say? It says we just need to do the integral from 1 to k of the square root of 1 plus the derivative. What's our derivative of 1 over x? Should be negative 1 over x squared. And so if we square that, that would be 1 over x to the 4th dx. And we can obviously get rid of the 1 and the minus 1 there to just give us k plus 1 over k plus this integral. Everybody good with part B? All right. Part C says we're going to take region R and rotate it around the x-axis, and we want to figure out what happens as k increases without bound. So find the volume or show that the volume is infinite. So all we've got to do is set up an integral with a limit as k approaches infinity of the integral from 1 to k of 1 over x, which is our function, squared. So pi times our limit. So pi times the radius squared, that's our disk if we're revolving it around. And then we just integrate. So we have pi, and we'll, since we've got a limit as k approaches infinity of this already, our integral of 1 over x squared ought to just be negative 1 over x. We'll go from 1 to k. We end up with pi times, I forgot to write my limit, negative 1 over k minus negative 1 over 1. And we end up with pi times 0 plus 1 or pi. Good or no? Fairly straightforward one. Cool. What else would you guys like to talk about? There's one more area one, but this one's like more like the AB ones. We can do this one if you guys want. It's possible that you might have a fairly straightforward one like this. Or we can do vectors, or we can do just regular motion, or what do you guys feel like? A motion one, a vector motion, or just a regular motion on a line? Regular motion on a line it is. Okay. Let's see, I have more ones. I think I just have the one, so I guess we'll do this one because that's the only one I've got. So I'll give you guys a second to read through it and see what's going on, and then we'll work through it. And this is a calculator one. All right. So for part A, we're asking what is the first time that Gwen changes directions? So she should change directions whenever her velocity is equal to 0 and actually changes signs, right? So since this is a calculator problem, it should be easy enough to figure out when that function changes from positive to negative or from negative to positive. So we'll just set v of t equal to 0 and figure out when that occurs. It looks like let's see here, I'm typing it in. I was typing it in while you guys are looking at it. Quite finished. Looks like I typed it in wrong. Shoot, let me fix it. Unless somebody else has already done it. Looks like the first time that happens is at t equals 19.146. Not 416. Oops. Everybody good with that? Pretty straightforward. Just see when it changes signs. Then the second part of that, find her average velocity. So an average velocity means the average of this function, which just means 1 over b minus a, so 1 over 19.416 minus 0 times the integral from 19.416 and 0 to 19.416. Of b of t dt. And so I'll adjust my thing on Desmos here on my phone, and let's see what we get. Looks like 7.264. Everybody good with the setup for that? All right, for part B, we want to know how far is she away from her position at t equals 0. Well, to find the displacement, because that's how far she is from her position, displacement ought to be the integral from 0 to 45 of the velocity function. And so let me just change my limits here real quick. Looks like that comes out to be 116.538. Everybody good with the setup for that? Part C asks for the total distance traveled. So the total distance ought to be the integral from 0 to 45 of the absolute value of v of t dt, right? The absolute value gives us the speed, the integral of speed gives us the total distance. So let me put in my absolute values here and see what that makes that become. Looks like 250.099. Everybody good with that? Setup there? All right. And then for part D, I need some more room here. For part D, we want to find the integral of her acceleration from 15 to 30. Well, the integral from 15 to 30 of acceleration ought to be v of 30 minus v of 15. And so all you got to do is figure out what v of 30 is and what v of 15 is. And that's a lot of things for me to type into business. So nobody really cares. I'm not going to type those in and get that exact value there. Did it ask us to explain that or no? Yeah, explain what the meaning of that is. So we're integrating acceleration. And so, acceleration is just the change in our velocity. And so if we integrate the acceleration from 15 to 30, that's just whatever the change in her velocity is over t equals 15 to t equals 30. And really, we should probably call this like a net change, right? Because if she sped up and slowed, she did speed up or switch directions in that interval. So it's the net change rather than just like the total change up and down, but how much it changed from 15 to when it's at 30, not all of the little small variations in between. Does that make sense to everybody? Fun little motion problem there. What else would you guys like to talk about? We could do, we got a couple of vector ones. We've got a slope field one. Riemann sum approximation, some just some of these area ones, some with charts, rate ones. What do you guys think? We got slope field. All right, Adrian's just directing us here on what we're going to do. So those of you watching this video on YouTube later, if you're mad about which problems we should do, it's not my fault. All right, so our slope field here. So first thing is to sketch your slope field. And I'll just mention again that if your slope field is not perfect, like we'll go on, it's not that big of a deal. So don't be too stressed out if your slope field doesn't, in your opinion, look perfect. It just needs to be pretty good. Make sure that you find the values where it's equal to 0 and make sure that those ones are definitely 0. So in our case here, this should be equal to 0 anytime x is 0 or anytime y is 0. So we should have 0, 0, 0, 0, 0. And normally having all the 0 slopes is worth a point on the test, and usually. And then all the other ones is worth another point. And then we'll just plug in the value. So if we plug in the 0.11, this is 1. It doesn't look like 1. Try to make it look about like 1. Doesn't have to be perfect though. -1, 1. So if the x is negative, it's going to stay negative. So it's going to be a -1. And then same thing over here, x is negative, but y is positive. It's still going to be negative because the y value is raised to the 4th. And then over here, y value is negative, but x is positive. It's still going to be positive. So there's your slope field. Pretty straightforward on sketching the slope field, I hope. Okay. Part B, find the second derivative. Yeah, okay, they didn't ask us to sketch. Okay, so find the second derivative. So for our second derivative, we will just take the derivative of this using the product rule with respect to x. So that should be x times the derivative of y to the fourth, which is 4y cubed dy dx, plus at y to the fourth times the derivative of x, which is just y to the fourth. And so then this becomes, if we replace the dy dx with the xy to the fourth, we've already got 4xy cubed times xy to the fourth plus y to the fourth. And chances are it's going to be helpful to us to factor out that y to the fourth just to see what things look like. We have y to the fourth, and then we have 4x squared y cubed plus 1. I believe, yeah, I think I factored that out right. 4x squared y cubed plus 1. If you don't factor it out, that's fine. It's not a big deal. And they want us to determine the concavity for all of the solution curves in the second quadrant. So in the second quadrant, we'll note that this is, and the best way to write this is something like x is less than 0, y is greater than 0. So if x is less than 0, 4x squared is still going to be positive, right? And if y is greater than 0, the y cubed is going to be positive. So 4 times a positive is positive. Plus 1 is positive. This is a positive, so we have a positive number times a positive number, indicating that all of these solution curves are concave up. Yeah, so in terms of showing your work, you would just say that x is less than 0, y is greater than 0. So this term is always greater than 0. It would be good enough. Or you could say a positive, it's a positive times a positive, or however you wrote it out. I mean, if you'd written it out originally as like 4x squared y to the 7th plus y to the 4th, you can just say that it's just two positive numbers being added together based on the signs of x and y, or whatever, what have you. I mean, really just writing x is less than 0, y is greater than 0, so this is greater than 0 should, I would imagine, be good enough. In fact, that I've seen some like this before, and their scoring guidelines normally just say something like, x is less than 0, y is greater than 0, so the second derivative is positive. They assume you can do the arithmetic. So part C, this is a good one for us to do because it makes us solve this differential equation, which is a possibility. So we're solving the differential equation xy to the fourth with 4 negative 1. So dy dx is xy to the fourth. And the point we're plugging in as our initial condition is 4 negative 1. So we got dy over y to the fourth is x dx. The integral of y to the negative fourth, that goes up to y to the negative 3, right? If this is y to the negative 4 goes up to y to the negative 3. We divide by negative 3, so this is negative 1 over 3y cubed equals x squared over 2 plus our constant. Plug in our value of 4 for x, that gives us 8 plus our constant. Plug in our negative 1, gives us positive 1/3 there. And so that gives us a constant of 1/3 minus 24/3, which should be negative 23/3. And then we just go back, negative 1 over 3y cubed equals x squared over 2 minus 23/3. And then we solve. So you can choose however you wish. You can either get a common denominator or not. If you don't get a common denominator, to take your reciprocal here, you just got to write it as like 1 over this whole thing. Personally, I prefer to get a common denominator. So I'm going to write this as negative 1 over 3y cubed equals, and this is going to be 3x squared over 6 minus 46 over 6. So I'll just put those together. And then we can divide by the negative and take the reciprocal all at once, I hope. We'll have y cubed equals 6 over 46 minus 3x squared. If I just throw that negative through the numerator, that becomes the denominator. And then we can cube root. Oh, I forgot my 3 there. Sorry. Yeah, yes, thank you, Adrian. I lost the 3. So we'll divide by 3 and then we'll cube root. So I'll just do that all in one step. That gives us y equals the cube root of 2, if we're going to divide the 6 by the 3, over 46 minus 3x squared. And just one quick little thing to be careful about. They don't normally ask when it's valid. Actually, let's see if they did. Yeah, they didn't ask. But you can find the interval of validity, set your denominator equal to 0. And what was I going to say? I was going to say something. If this becomes a square root, remember that it becomes a plus or a minus. And in order to figure out if it's the positive or the negative, you got to go back to your initial condition and make sure you choose the one that makes your initial condition true. Right? Same thing with, you have like an absolute value over here. When you take the absolute value off, you get a plus or a minus. So make sure you go back to the initial condition to determine which the plus or the minus you actually want. Everybody good there? That was the last part of that one, I think, right? Yeah. All right, what else? We got a couple more minutes here. Let's see. Still got a couple of vector ones down here. We've also got this one, approximating using a Riemann sum, and then just doing some integrals. I did that one. Another chart with a Riemann sum. Graph, ones with graphs. Anybody have anything they want to do? Another motion problem. The exact opposite of whatever Adrian says. I don't know. Nobody has a preference. I'll just pick one. Or if you guys are done, we can be done. We only got 10 minutes to go. So if you guys feel like you're good, that's fine. But if you want to go through one more or two more if we have time, I'm happy to. The Riemann sum one actually says, okay, somebody else has made a decision. This one? There's another one with a Riemann sum also, but is this the one you're talking about? Vector up there. All right, perfect. Okay. Glad we got a decision here. So first off, we're going to approximate the Riemann sum using these subintervals. Or approximate the integral using the left Riemann sum of these subintervals. So we'll note that this one has a length of 3, this one has a length of 4, and this one has a length of 4. So they have different length subintervals, so we got to make sure we're careful about the lengths of each of them. The first one should be 3, a length of 3, times the value of our function at the left endpoint. So 3 times f of 1, and then 4 times f of 4, and then 4 times f of 8. And so f of 1 looks like it's 4, so that's 12. F of 4 looks like it's a fourth, so 4 times a fourth is 1. And f of 8 is 4 over 64, that's a 1/16. Times the 4 should be 4/16 or 1/4. So we've got 13 1/4 there as our answer, which, what is that? 13 times 4 is 52. So that would be 53/4. Any issues there with part A? Okay. Part B, find the value of the integral from 1 to 12. That should be easy. I'm going to put the 4 out in front because there's no reason to have it in there. Integral of 1 over x squared or x to the negative 2 is just negative 1 over x. So we've got 4 times negative 1 over x from 1 to 12, which ought to be 4 times negative 1/12 minus negative 1. And what does that come out to be when we simplify that down? So 11 twelfths, right? Negative 1 twelfth plus 12 twelfths is 11 twelfths, 44 twelfths. 44 twelfths ought to be what? Divide that by 4, 11 thirds. All good there or no? All right, part C, find the value of the integral from 1 to infinity. So we got another improper integral. So remember, this is the limit as a approaches infinity of the integral from 1 to a of 4 over x squared, right? And we should know that this should converge, right? We should know that this integral exists because this is how we prove the p-series test, right? Or one of the values in the p-series, right? The power is greater than 1, so it should converge. So when we integrate this, we end up with the limit as a approaches infinity of negative 4 over x from 1 to a. And so that ought to give us the limit as a approaches infinity of negative 4 over a minus negative 4 over 1. The negative 4 over a is 0 as a goes towards infinity. The negative 4 over 1 is just 4. Everybody good there with part C? All right, and then part D, I guess a new page because this one's going to take a little bit more room, I think, based on what they're asking us to do. The integral from 1 to 12 of ln, or f of x times ln x, so 4 ln x over x squared. And I'm just going to pull that 4 out to the front because there's no reason to keep it in there if we don't feel like keeping it in there. If you want to keep it in there, you can. Should be pretty easy to integrate the x squared. So let's make that our, the 1 over x squared, our dv, which will make our u ln x, which will make our v will be negative 1 over x, and our du will be 1 over x. So we've got 4, and then now we've got an integration by parts here. I guess I should have said this was an integral that we probably should recognize needs to be done by integration by parts. Yeah, I didn't actually say that, but everybody agree that that's one that should be done using integration by parts? I hope. Unless there's a simple u sub, usually ln x has to be done by parts. So we've got 4 times u times v, so that's negative ln x over x. And then minus the integral of v du, which should be the integral of negative x squared. Sorry, negative 1 over x squared dx. And that's still 112. We've now got 4 times negative ln x over x plus, if we pull that negative out, and what's the integral of x 1 over x squared? That should just be negative 1 over x from 1 to 12. So we should have 4 times negative ln 12 over 12 minus a 12. And then minus, what do we get there? If we plug in 1, this whole first term is 0. And then if we plug in 1 there, we get 0 minus 1. So it looks like we've got, if we pull this 4 through, we've got negative 4 ln 12 over 12, which should just be negative ln 12 over 3 minus 1/3 and then plus 1. I didn't multiply either of those ones by 4, so minus, it didn't multiply that one. It didn't multiply this one, plus 4. There we go. So negative ln 12 over 3 minus 1/3 plus 4, which should equal 11/3 minus ln 12 over 3. Everybody good with that one? So nice little integration by parts. All right, that's the last one we're gonna do. And just gonna mention a couple of things at the end here, just to keep in mind as you're going through. Number one, on the calculator problems, make sure that you do not round anything until you get to your final answer. When you get to your final answer, you can round to 3 decimals or more if you want, but don't round any of the intermediary values before you get to your final answer. Otherwise, you'll end up with something that's slightly off at the end. When they tell you to justify your answer, you need to do that, okay? It helps to write out a little sentence, but most of the time, just having the math is good enough. But, it's nice to say, it's an underestimate because, the function is increasing and it's a left rectangular approximation or something like that. So just make sure you're clear and specific with your explanations. If it says put units, don't forget to put units, because if it says units, it means that there is a point associated with the units. And I know I've said this in the past during class, I believe, but if, now I just forgot what I was going to say. If you are working through a free response question and you decide that what you've done is incorrect, don't go and erase it all. If you're going to move on to something else, like just leave it there, just in case you don't have time to come back. But also, if you do come back and rework it, you don't need to waste your time erasing. Just put an X through it or something, and they'll know not to look at it. But make sure that what you've done the second time is better than what you did the first time. If what you do the second time is worse than what you did the first time, if you don't like it, then just X out the second thing you did. But if you erase all the first stuff and then what you did the second time is worse, then you're kind of you're putting yourself in a bad situation. And skip multiple choice questions right off the bat that are going to take you more than a minute to do, and then come back to them later. Go through those first 30 non-calculator multiple choice and do all the ones that are just going to take you a bit, and then get all those nice easy points, and then come back later and do the more difficult ones that are going to take you 3 or 4 minutes each. Same in the calculator multiple choice section, do the same thing. And remember that when you're doing free response questions, you can use your calculator to evaluate a derivatives at a point. You can use your calculator to evaluate a definite integral. But you need to write, if you're looking for f prime of 7, write f prime of 7 equals, and then put the answer. Or if you're looking for the definite integral from 2 to 5 of some function, write the integral from 2 to 5 of f of x equals, and then put the answer. But make sure you write what you're having the calculator do. Same thing if you're using it to find a point of intersection. Make sure you write f of x equals g of x, and then use your calculator to figure out when that's true, and write at x equals the values that it's true at. Same thing if you're using it to find an x-intercept or something like that. Make sure you write out what you're using your calculator for. Write out the equation that you're having it solve, or write out the integral that you're having it solve for you. That makes sense to everyone? Cool. I'm sure you will all do wonderfully on Tuesday. If you have any questions between now and the test, feel free to email, send me a reminder, or whatever works best for you. And I will get back to you as quickly as I can. I'm sure you will all do wonderfully and make yourselves proud and whatnot. Other than that, I've got nothing else. That is it.